Come in. Is this yours? It doesn't matter.
Okay, our next speaker is Helger Lipmaa from Universitāte Tartu.
Hi all. I think most of the people already have seen me several times. This is my third year to give a talk in Riga. And this time I'm going to talk about the paper that I'm kind of still finalizing. But also in the beginning I will try to give some kind of like introduction, like what is this stuff and why this is necessary. It's not related to quantum, but the interesting thing is that I use some mechanics or some techniques that at least Alexander's and I think also Andres and maybe some other people here have been using in a completely different quantum setting. So I'm going to explain what I'm working on. It's so-called non-interactive zero knowledge. I'm going to motivate zero knowledge. I'm going to motivate non-interactive zero knowledge. And then also motivating why it's interesting to do this NIZK stuff for NP-complete languages. I'm going to present main results and then some kind of like outline of the approach, but I'm not really sure how much I can do with 1 hour. So maybe I will skip quite a lot of slides. Let's see. The paper is online in our ePrint archive, but the current online version is somewhat outdated. So, the main important stuff here is zero knowledge. Dominic already explained zero knowledge from his own viewpoint. My own viewpoint is somewhat different. Or like my approach to why I'm interested in zero knowledge is maybe somewhat different. So the idea is that if you have any kind of a protocol between 2 or more participants, if everybody is honest, then it's very easy to design protocols that do whatever you need. So for example, if you want to do some kind of like database transfer, you go to the database, you say that you want this element, database sends it back to you. And then you do something with this element, maybe you continue several other rounds. The problem is what happens if parties are not honest. So for example, you get the wrong element from the database, or maybe you want to protect the privacy of different parties. So a general way of dealing with that kind of issues is to use zero knowledge. So to every step in some kind of like a more complex protocol, you add a zero knowledge proof. So here Alice is on the left, the bad Bob is on the right. Alice sends some message to Bob and then attaches to it the zero knowledge proof that this message was in some sense correct. Let's say it was really like a valid index to the database. Maybe you want to protect privacy, so this index is not sent as a plain text, it's sent in an encrypted format, but the zero knowledge proof in this case shows that this index is actually from the valid range. You don't want to have like some kind of like out of bound.x, etc. And then Bob sends you back something and attaches a zero knowledge proof that actually he performed correct computation, and etc. Alice responds with some message, adds a zero knowledge proof, etc., etc. And the zero knowledge proof, if you verify the zero knowledge proof, then the basic idea is that you get convinced that this another party did something correctly, but you don't get to know anything else except the truth of the statement, that the input of this other party was, let's say, from a correct language. Correct range of indexes, correct database, whatever. Then in many cases like that, you might have some kind of arbitration round. So at the end of the protocol, maybe Bob detects that Alice did something wrongly and then wants to go to the judge and then claim it. And then Alice should also be able to prove to this judge that her behavior was correct. One concrete example that I always give in Estonia is e-voting, because we have e-voting. So for example, Alice could be the tallier who's counting the votes, and then later has to prove to a judge that the votes were actually tallied together without revealing any individual vote. So it has to be like privacy preserving zero knowledge proof. Another application that very well fits with the stuff that I'm doing is something called verifiable computation. So assume that Alice has a very small computer, like very, very tiny. Then Alice wants to perform some kind of a complicated computation. What exactly it could be, you can imagine. I'm not really sure what are the very good examples, but maybe some kind of scientific computation, maybe feather prognosis, maybe something simpler, but still something that you cannot do like with this very small computer, or maybe even with this one here. So there are many providers that provide that kind of services already. I think Amazon provides something like that. You outsource your computation to Amazon servers, and those servers compute the result to you, and then give back the answer, and then charge you by the time or amount of work that the servers do. The problem here is the same. Can you actually be sure that Amazon behave correctly? Is the answer correct? So again, in this case, you can add a zero knowledge proof where Amazon, together with the answer, attaches a proof that this stuff was actually correct. And zero knowledge maybe sometimes is not really so necessary here. It depends on whether actually this second argument of f here, whether this is, well, why is here like Amazon's input, whether this is actually something private or not. So maybe all the input is provided by Alice, so maybe zero knowledge is not necessary at all, but it has to be a proof of correctness. And because this Alice is very tiny, like a mouse, then this verification obviously has to be much faster than the original computation of this function. Then there are many methods how to construct zero knowledge proofs. Dominic already gave a talk about like he was looking about looking at interactive zero knowledge proofs, where the zero knowledge proof itself, it's several rounds. Alice sent some kind of like commitment to Bob answers with a challenge. Alice sends third message, maybe there's fourth message, maybe even more. So this is like the most standard way of doing it, and in some sense also the most efficient, at least computationally. But there are many problems with this approach. One of them is that every time when you want to verify whether Alice computed the stuff correctly, you actually have to interact with Alice. So assume again this e-voting scenario. Let's say Alice is a voter and has to prove that this vote was computed correctly. So let's say that it encrypts a valid candidate name without revealing, of course, which candidate it was. And maybe something happens in the tallying phase. You find out that some of those stuff is incorrect. So you would like to go back to Alice as a voter and ask her to prove that this stuff was done correctly. So if you have interactive zero knowledge, you have to interact with Alice every single time. And this is, well, at least in this application, but in many other applications, this is completely impossible because a voter might just vote and then go and party. So this is, you don't really want to have interaction in, I think, I don't know, most or many or several applications in practice. I think other problem with here is that, as Dominic already explained to you, there are many subtle issues. So, well, it didn't really go into those issues that, like, if you just have this interactive zero knowledge, it's easy to construct a protocol that is secure if it's run in isolation. But if you want to if you have a real-life situation, you have many different zero-knowledge proofs of many different also protocols running in parallel, then you get into a real mess. So another thing that he explained was that in quantum case you have a lot of problems. You have this rewinding, you want to copy something, blah, 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 it doesn't really work. And I think it's boring. It's boring in the sense that we don't need it in practice anyways. So in practice I would like to have non-interactive zero knowledge. So why bother? So what is non-interactive zero knowledge? In the case of non-interactive zero knowledge, Alice does something and then to this something adds a bit string, and this bit string is a valid proof that the computation was done correctly. So Alice computes a bit string, sends it away, and this same bit string can be verified by possibly many verifiers without any further interaction with Alice. And that's very nice in practice, because now you don't assume that Alice doesn't party, for example. What do you want from non-interactive zero knowledge? Well, basically you also want it from interactive zero knowledge, but the techniques are different. So you have somewhere of a common input x. Let's say Alice has, actually there are private inputs, there are common inputs. So let's say let's take something mathematical. X is a large number, and Alice wants to prove that she knows how to factor it. So X is this large composite number. Then witness is something that Alice knows and Bob doesn't know. Witness is just the factors. Then Alice computes this phi, which is a proof of the fact that X is a composite number, let's say. And then you have several objectives: correctness, soundness, and zero knowledge, which I'm going to explain in the next slide. And as Dominic already mentioned, in the case of zero knowledge, you kind of prove it by simulation. It's the standard technique. So how do you do it? So what do those requirements mean? The first one, which is the most obvious, is correctness. If both Alice and Bob are honest, if Alice did the computation correctly, then Alice should be able to convince Bob, if Bob is also honest, that this computation was correct. That means that Bob should accept the proof of Alice, and here Alice knows the witness. Soundness, on the other hand, means that if Alice is not honest, then, or let's say not Alice is not honest, but let's say X doesn't really belong to this language, let's say X is not really composite, then no Alice should be able to convince honest Bob. This means that if X is incorrect, not in this language, then verifier shouldn't accept the proof of any possible proof of X and any possible witness. So this is kind of a common things what you want to improve, like correctness and soundness. But then you also have this privacy thing, zero knowledge. You wouldn't like this proof to reveal anything about Alice's witness, except the fact that this X itself belongs to the language. So Bob should get convinced of this, but nothing else. And the way of doing it is by simulation. So you basically construct a machine that should be able to construct exactly the same proof as Alice did, but without knowing the witness. So because the simulator doesn't know the witness, then this proof doesn't reveal anything about the witness. But obviously here is a catch, because the prover, when prover actually constructs this proof, prover should know the witness. And now you have this case that the simulator should be able to do the same, but without knowing the witness. So the catch is how to guarantee soundness and zero knowledge simultaneously. And the common method is that you give some kind of extra power to the simulator. You give something that the prover doesn't have. In the case of interactive zero-knowledge proofs, the simulator has the power to rewind the prover of the verifier. But here in the non-interactive case, there's no rewinding, there's only one round. So there has to be some kind of like extra power, some kind of a different extra power. And if simulator doesn't have any extra power, then you cannot really do it because you have those contradicting requirements that one guy should be able to construct this proof only knowing witness, and another guy should be able to do it even without knowing witness. So this knowledge of witness in the case of simulator should be replaced with something else. And the most standard, most best accepted model here is something that is called common reference string. It's assumed that during the protocols, parties have access to some honestly generated common reference string. You can think of it like as being some kind of like public key. Somebody has honestly generated a public key, it's posted somewhere, and then everybody takes something from this public key and does something with it. And this is all that the honest parties know. But in simulation, simulator has this extra power. And the extra power is actually, basically, intuitively, it means that the simulator knows the corresponding secret key. So knows some kind of a trapdoor, something extra on top of the CRS, and given this extra, well, the extra doesn't depend on the input, it doesn't depend on the witness, but it somehow enables to maybe decrypt something or do something like that, so can actually construct the proof without knowing the witness. And so that's the extra power. Still, the simulator knows this secret key, but doesn't know the witness, so the proof doesn't reveal anything about the witness, anything about the input, except the fact that the input belongs to the language. And people are arguing about it if this model is reasonable in practice or not, because if you again like have some kind of like practical applications, then somebody has to generate the CRS without knowing public key, etc. But it's kind of a good question that this can be done, but this is I would say, the best model that we have. So simulator is the guy who knows the secret key here. And then you have several other things. Not only you have this model, CRS model, which is like non-standard, it's somewhat trust-based, but then the question is also different cryptographic assumptions. So you can try to build zero knowledge based on one-way functions, based on something more complicated, etc., etc. And the assumptions that are used in constructing the efficient non-interactive zero knowledge proofs are pretty strong. It's basically knowledge assumptions. The assumptions is something like that, that if you can compute, well, yeah, I'm not going to explain it much, but basically the idea is that if you can compute the exponentiation of something, then you actually know the exponent. Well, it's more complicated by that, and there are papers that show that this kind of assumptions are actually necessary if you want to get the efficiently verifiable NIZK. I'm not going to explain it more. I think this is also, for this audience, this is not so interesting, but Jens Krott, who is one of the, I think the best known guy who works in this area, and this year he had a talk in Bar-Ilan Winter School where he was presenting all those previous schemes. So as you notice here, you have two axes. One of them is the efficiency, like the x-axis. Efficiency here is the length of this proof compared to the length of the input. So linear means that the proof is approximately as long as the input. Sublinear means that the proof is shorter than input. Superlinear means that, well, it's longer, of course. And then the first schemes were like really inefficient. And the second axis is the assumption that you use. If you have weak assumption like trapdoor permutations, then you can do something that is, well, relatively inefficient. And then if you have better assumptions or stronger assumptions, then you can get more and more efficiency. And as you notice here is like a white square. And this is the white square that is due to those impossibility results. So those two papers basically show that if you want to get something that is more efficient than linear, then you have to use one of those very strong assumptions. And because my own interest is in doing something more and more efficient, I'm just using them. And here's some kind of a list of like how efficiency of previous papers, which are so if you don't work here in this area, maybe they are not so interesting, but kind of maybe they give you some kind of idea like what is the efficiency that you can get. So there's this CRS that somebody has to compute. So n is, let's say, the input size. Then the work that I have in this paper, the CRS length is n log n, which is the same as in a paper that is now going to be published in Eurogroup. The length of the proof, on the other hand, is only 7 group elements. And in my case, the group, well, it's not a big improvement, so it's I'm just using asymmetric pairing, so every group element is very short, 7 group elements is 58 bytes. So it doesn't depend on the task that you're doing. The proof is always 58 bytes, independently on the input size. And then prover's computation is n log squared n. So it's not linear, but pretty close to it. And verifier's computation is, so n is the, let's say, if you have a circuit, then n is the number of gates in the circuit. But here, the verification complexity, this is not the number of gates in the circuit, it's the number of the inputs to the circuit, which is much, much smaller usually than the circuit size. So you only need to do like number of exponentiations that is linear in the input size. So a bit motivation why you need this stuff. So what I'm doing in this paper is actually non-interactive zero-knowledge proof for one concrete NP-complete language. So let me recall that NP-complete languages are the most difficult languages in the NP class. So if you can, for example, if you can solve like one NP-complete language efficiently, you can solve all NP languages efficiently. And classic, like the best known NP-complete languages are something like SAT and traveling salesman, etc., etc. What I'm studying here is circuit SAT. So is this given circuit SAT is viable? So because of those generic results that those are the most difficult languages in NP, it means that if I can do something efficiently for those languages, I can actually do something efficiently for all NP. But the catch is here that the reductions are polynomial, so actually it's not going to be that efficient. It's the reduction is going to add some overhead. So this is not maybe not very good motivation. But for me, this second part is much more interesting. So I mentioned verifiable computation. So you want to other party compute something and then proves to you that this computation was done correctly. So this can also be written in the language of circuit SAT, and then this other party can just send you back a short proof, seven group elements, that this computation was done correctly. And because I'm working with an NP complete language, then this can be basically done for every efficiently computable task. And always this proof is going to be 7 elements. And there are probably other possible applications. I haven't really had time to think about them, but I hope there are. So what's the task? Concrete language? Like I said, I'm interested in whether the language is circuit SAT, whether this, the question is you are given a description of an arbitrary circuit, and you want to know whether this circuit is satisfiable. So for those who don't know what is a circuit, so circuit is basically it has an underlying directed acyclic graph. Every node of the graph is labeled by a function, and then there are inputs on the bottom and output on the top, and then you have obviously this natural computation process. You start with the inputs, you apply this function, the output of this gate goes upwards to the next gates, and then you basically do a bottom-up computation, and then you get the output. And then the circuit SAT language is basically you're asked whether there's an input, such that if you give this input to the circuit actually outputs 1. And again, you want to do it in zero knowledge, so this input should not be leaked. So the only thing that is leaked is that there exists such an input, and nothing about the intermediate computation should become public. So this maybe looks somewhat complicated already, but at least in if you work in theoretical computer science, this should be the obvious stuff. Although I found out that people who do practical computer science don't really know what is a circuit. So they think it's the stuff that is inside the computer, which are somewhat different. So what's the very general idea of the concrete approach of how to, like and the previous paper that my work is based on, like how it approaches this problem, is that so basically the protocol itself consists of 2 completely different parts that obviously later have to be like somewhat like glued together. The first part is non-cryptographic. So we basically construct circuit checker that doesn't like protect any privacy or don't do anything cryptographic, but it's just somehow a nice linear algebraic way of checking whether this circuit is satisfiable or not. And this part doesn't, like I said, it doesn't protect privacy. So if we can divide this part into 2 different parts. One of them is called gate checkers and then wire checkers. So there are gates, those yellow thingies, and then there are wires in between, or edges and vertices and edges if you're used to more to gate graph theoretic descriptions. So what do those things do? The gate checker basically checks that every individual gate outputs given concrete inputs outputs a correct output. So this concrete function that this gate does has been computed correctly. And then wire checkers basically verify that every wire is consistent. This means that, for example, this output of this gate number 2 is actually equal to the input of the gate number 3. And all those gate checkers and wire checkers, they are basically, well, I'm going into it in a couple of slides. They are span programs. You can think of them as large matrices. They do everything in parallel. There's one step that verifies the correctness of every gate in parallel, and another step that verifies the correctness of every wire in parallel. And because wires and gates, if they are both correct, then all this computation is correct. And so you know that this circuit actually computes the output correctly. And in this step, in gate checkers, we use span programs. And in wire checkers, we use in this paper that my work is based on, they called it quadratic span program. So you can use this terminology, but basically what you use here is high distance linear error correcting codes. And then at the end, you add this cryptographic part. Like I said, everything previously was non-cryptographic. So you have some kind of like large linear algebraic stuff. But you want to also protect privacy. So for this, you need this crypto. And another thing is that this linear algebraic stuff by itself is not really efficient, because you have to communicate long vectors, and at the end you don't get anything sublinear, you get like linear communication. So we want to not only get privacy, but we want to somehow compress the output. And we can compress the output if we assume that, well, basically the assumption is that if some kind of a body knows a compressed output, then he also knows the corresponding uncompressed part. So if you use those knowledge assumptions, you can do this compression somehow efficiently. I think I'm not going to be able to talk at all about this cryptographic part, so I'm going to explain this non-cryptographic part. So your first part, gate checkers, they check every gate individually, but it doesn't, this part doesn't actually check that this output of this gate is equal to the input of the second gate. So you have wire checkers that also check the consistency of different wires. And then you have this cryptographic sugar. So what is span program? It's an alternative computational model. Like circuit was already like one model, which I think well, if you work in theoretical computer science, then you always start with Turing machines. I actually like circuits better. I think they are nicer. It's a nicer model. Span program is not that well known, but it's basically also something, a model for computers that performs computation in some kind of a way. They were defined by Karchmer and Vickerson in '93. They have several different applications, kind of a weird applications in the sense that there doesn't really seem to be anything in common between them. So you can prove different lower bounds by using span programs. You can construct quantum algorithms in some weird model that Alexandros is going to explain next. Then you can use them in crypto in several ways, like if you do secret sharing, you can use span programs. And now here is non-interactive zero knowledge. And there are probably more applications, but it's not really like a widespread model. So before I started to work on this, I actually didn't know anything about them. And like I said, Alexandros is at least working a lot on span programs. At least I think Andres has also done something. I'm not really following what other people are doing, so I'm sorry about that. So what's the idea of span program? So again, like in the case of circuits, it was very easy to explain. Like you have like gates, and every gate computes a function. The function goes upwards, and then every further gate has inputs and outputs, etc., etc. In the case of span programs, it's not so intuitive. So if you formally define, you have to define syntax, you have to define semantics, etc., etc. So basically, I think I'm going to just explain it by using some of the examples. So every span program is basically, it's a matrix, like this gray part, then it's a target vector, this T, and then every row of this matrix below is labeled by some literal, some variable or a negation of some variable. And for example, this span program is computing NAND, and this is computing XOR. I think I will just omit this formal definition. I will try to give some kind of intuition by example. So why this work, or how this computation is actually done. So this is OR, I think simplest span program probably, except maybe identity. So what does it mean is that you say that, the idea here is that you want to check whether the target vector is in the span of those rows of this matrix that correspond to the corresponding assignment. If it is in the span, then the output of the function is 1, otherwise it's 0. So for example, in the case of OR, you have two vectors here, 1 and 1, and then you have target vector. And you want to check whether this one is in the span of those two. So the question is, so this is one vector, V1, V2 is another vector, T is the target vector. So what does it mean to be in the span is that there exists some coefficients A1 and A2 such that this holds. And now, because V1, V2, and T are all equal to 1, this is equal to the requirement that A1 plus A2 is equal to 1. So when does this latter hold, A1 plus A2 is equal to 1? It holds exactly when at least one of A1 and A2 is non-zero. So it's basically ideal. So it's an OR operation. So if it's sufficient for one of them to be non-zero. And 0, 0, x and y are both equal to 0 is not consistent input here, or it's not accepted, because in this case, your 0, 0 is not like if you're working with this input assignment, then you're basically, you can't use either of those rows in the sum. So you basically have like empty vector or 0 vector is equal to the target vector, and this can never hold. So 0, 0 is not accepted. So it's a correct like OR. Another example is AND. It's only slightly more complicated. Your target vector is 1, 1, and then you have two vectors. One of them is labeled by x, another one is labeled by y. So this vector is 1, 0, and this is 0, 1. So you want to have that one coefficient times 1, 0 plus another coefficient times 0, 1 is equal to 1, 1. And it's easy to see that this holds exactly when a1 and a2 are both equal to 1. So the target vector is in the span of those two vectors here if both vectors are non-zero. So it's an AND function. Yes?
I don't understand why the thing before wasn't XOR.
Why it wasn't an XOR?
Because if A1 and A2 are 1.
Well, you don't care about whether they're 1, you care about whether they're non-zero or not.
Ah, okay.
So this holds exactly when at least one of them is non-zero. So this is actually something that we can use when we design cryptographic protocols. We don't have to verify whether this is equal to 0 or 1. We just have to verify whether it's 0 or not. And this is, in many cases, it's simpler. And analogously, you can if you go forward, then you can see that, for example, 0, 1 is not accepted, because in this case, in the sum, you cannot use the first row. You can only use the second row. So some coefficient times 0, 1, this can never be equal to 1, 1, independent of the coefficient. And then you can just do the case analysis and look all other possibilities. And then if you have those span programs, you can compose those span programs. You can compose them by like in the case of circuits. Basically, if you have two circuits and then add on the top of AND or, then this is composition of circuits. And similarly, you can do a composition here. The composition will increase the underlying matrix. So I'm not going to explain it here why it works like this, but if you have like one span program like this, another span program like this is one matrix, another matrix, one target vector, another target vector, one labeling, another labeling, then the AND composition is just like this. You take all vectors from here, you put them here and add zeros to them. And then you take all vectors from here, add them here, and prepend them with zeros. And it's so easy to see that because if this is an accepting span program, then you get there exist those coefficients that make this to be in the span of this, and there exist the coefficients that make this to be in the span of this. Then the AND is also correct. So maybe it takes a couple of more minutes to completely understand it, but I really don't have that much time here. And OR composition is something like this. Again, you start with two different span programs. In this case, the span programs have to get efficient OR composition. You must assume that the target vector is in a specific form. It starts with 0 and then everything else. Sorry, it starts with 1 and everything else is 0. And then you have the labelings and the stuff downstairs, and you construct OR composition like this. So every time you compose two span programs, this matrix here is going to have dimension. So the size is the number of rows, the dimension is the number of columns. So the size is basically going to be the sum of sizes, and the dimension is basically going to be the sum of dimensions. So in some sense, every time you do this, it all doubles, but the idea is that the dimension and size of the number of rows and columns is going to be linear in the size of those small operations that you at the end compose. So you can imagine that you construct an efficient circuit or efficient Boolean function, and then you will find out how to, you have some kind of a function that for which you want to construct span program. You write this function down as an efficient circuit, or by using some other maybe formula representation, and then you just compose a span program out of the small span programs to get a span program for this larger one. This, unfortunately, one reason why span programs are not that widely used is that at the end, the span programs are not going to be very efficient. So you can basically, I already slipped this word, so you can start with a formula, and from formula representation you can construct efficient span program, but you cannot write everything as an efficient formula. So span programs by themselves can only do like relatively simple stuff. So when you want to do something more complex like NP complete languages, you need to add more stuff to it. So span programs by themselves are not sufficient. Okay. So the next step here is that, like I said, we want to check whether this circuit has been computed correctly. So circuit is this graph. Every node is some kind of like small simple function. And as people working at least in theoretical computer science know, you can basically assume that every node is a NAND gate. So it doesn't really matter, it just makes it easier. I don't have to go through all the different cases. So let's assume that we want to deal only with NAND gates. So NAND is this operation, NAND of x, y is equal to 1 if either x is 0 or y is 0. And x and y are Boolean, so either 0 or 1s. So it's a negation of AND. And we don't really want to compute the circuit, we want to check the output of the circuit. So we actually want to check whether the output of NAND is computed correctly given the inputs. So we have this checker function C, x, y, z. This is equal to 1 exactly if NAND of x, y is equal to z. This comes out to be a relatively simple function, although it took me some time to think about or find out a really efficient span program for it. So the way how I finally did it is that I wrote down this conjunctive normal form for this C, which is like this, or, and, blah, blah. And then I used or and compositions to construct a span program like this. And then I used one hand trick to actually get rid of one row. So this is somewhat more complicated than those and or programs, because you also add rows corresponding to the negation of variables. So, for example, the idea is that you can get target 1, 1, 1, for example, in the case where x is equal to 1, y is equal to 1, and not z is equal to 1. That means z is equal to 0. And you can just make a case analysis saying that this presentation is correct. So this NAND program has 6 rows and 3 columns. So size 6, dimension 3. And then so again, we want to do this for every gate checker. So we use this previous AND composition to construct a large matrix that does the same stuff for all gates in parallel. So here is a gate checker for one gate, another gate, etc., and everything else is 0. Again, there are many details. Welcome to the world of NIZK. Also, here this comment, like I said, every circuit can basically compute it by using NANDs, but it's actually very easy to also compute to construct span programs for OR checker, AND checker, etc., etc. I did it for OR and AND checker, but it's just a boring work somewhat to write it down for all possible binary functions. So now the question is, okay, I'm going to explain wire checker, then I'm going to skip the cryptographic part, and then I'm just going to give the efficiency results. So why exactly we need wire checker? So like I said, there's a necessity to verify that the input of some gate, some wire is equal to the output value of this wire. And why this is necessary? So let's say, well, we have a circuit, and in the case of circuit, every gate might have fan out that is larger than 1. So the output of this gate might be input of several other gates. Let's just look for the simplicity of the case where the fan out is 2, so you have 1 input and 2 outputs. And let's say the output of this gate is this Z, which is NAND of X and Y's. So this value Z here, and the corresponding value here is, let's say, X, and here it's Y. So you basically want to check that this Z here and X here and Y here are all consistent to each other. So what's the problem here? The problem is that you have here rows that are labeled by the negations. So like I said, for example, NAND, you can get T by setting X equal to 1, Y equal to 1, and Z equal to 0. And this gives you one here, and 1 here. You get target vector. On the other hand, this here you could set, for example, let me see, X equal to 0, for example, like this. Or let's say not X equal to 0, but also Z equal to 0, and X and Y equal to 1s, and you get also target vector. But here, this X should be equal to this Z. So if you just individually check every gate, you get that every gate is correct. But here, this output value of this wire would be 1, and here the input value of this gate would be 0, and the gate checkers just accept. So you must somehow verify that those this Z is equal to this X here and equal to this Y here. So what does it mean is that you shouldn't use rows from those matrices that correspond to inconsistent values of the same variable. So if you use, for example, Z from here, because Z here is equal to X here, so if you use this row here, you shouldn't be using yellow row here. So you either use only green rows, or you only use yellow rows, but you shouldn't use green and yellow at the same time. So you must have some kind of like mechanism to check this. So either all coefficients of green rows should be 0, or all coefficients of yellow rows should be 0. So again, maybe somebody who works in that kind of problems can immediately spot it. For me, it took some time, but then I found out that if you know a bit about error correcting codes, then this is actually trivial. So what's the idea? So you want to check with some vector. Let's say this vector corresponds to the yellow coefficients corresponding to yellow rows, whether this vector has only zeros or it has at least one non-zero value. To make this verification simpler, we want to have like a mystical operator that takes all zero vector to all zero vector, but in the case where there's at least one non-zero, then the output vector has 50% plus 1 non-zero inputs. And this is something what you do with error correcting code. So you have a linear error correcting code with such property that if X is a 0 vector, then the output of this code is 0 vector. If the input vector is not 0 vector, then the output has at least D non-zero coefficients. And if you set D so that D is 50% plus 1, then you're done. And you can use many standard error correcting codes. Well, we need something that is linear, and we need something where the distance is at least half of this n. So distance is d, and this first parameter is 2d minus 1. And there are many different codes that you can use. For simplicity and for efficiency, I use Reed-Solomon codes. I'm again not going to explain what exactly they are, but this is their function. So if there's zero vector, then output is zero vector. If at least one input is non-zero, then more than 50% of the outputs are non-zero. And we have this new guy, Vitaly Skacek, in our department, who's exactly working on the error correcting codes. So how we use it here is that we want to check whether all coefficients of green rows are all zero, or all coefficients of yellow rows are all zero. So maybe here it's again already obvious from this construction what exactly I'm aiming to, but the idea is something like this. So I would like to have this kind of situation. So if I use a code like this, then what happens is that if x is not equal to 0 and y is not equal to 0, then the outputs both have like 50% of plus 1 non-zero elements. So this means that there exists at least one input so that the outputs are both non-zero at this point. So for example, if x is this and y is this, then this Reed-Solomon code maps x to this and y to this, and they are both non-zero in, let's say, in this case, in this first coordinate. But in general, such coordinate exists. So, so the kind of ideas that we use linear error correcting code. So to take these vectors, or the vector of coefficients that correspond to this gate, vector of coefficients that correspond to this gate and to this gate, then we use the code such that if at least one orange row is if at least one orange coefficient is non-zero, then 50% of the output are non-zero, and if at least one green is non-zero, then 50% of the output are non-zero. Also, we use linear error correcting code, which means that we can basically compute the code by using linear algebra. We take the input vector, multiply it with some matrix, and get the output vector. This is also important to get good cryptographic efficiency. So we get those are the green vectors here, or green coefficients here, like y of left, z of down, and x of red, and x of right, and those are yellow ones. And then we just apply those matrix, well, basically generator matrices of the code, and we get that like from 3 inputs we get output of length 5, where at least 50% are non-zeros. And so if we do it in both cases, we get that at least one coefficient is, there exists at least one coefficient where the output is 1, not 0. And then we use kind of define a computational model where this is relevant. So, but basically, intuitively, this is sufficient to understand. So what is going on? If this y is inconsistent, then at the end of this operation we get at least one row where both vectors are equal to 1, and then we somehow define an efficient cryptographic way of detecting it. So actual construction is somewhat more complicated, but I'm not going to skip it. So and then we have to aggregate wire checkers, so we have to do this for every wire. And we do it again by using hand composition. We basically have only we have this aggregate gate checker that has those small gate checkers, and then everything else is 0. And then we have aggregate wire checker where there's a small number of non-zero elements and majority of elements are zeros. And then we just compose them. So the end matrix will be something like this. There will be actually two matrices. One of them corresponds to those green rows before, and another one corresponds to yellow rows. But I'm simplifying here a bit. So this part here is one gate, another gate, third gate. Zeros are not filled in. So you can see that there are very few ones. Everything else is zero. And then there are those Reed-Solomon generating matrices that check every y individually. And they are also like only very few non-zero elements. The important thing here is actually that even if the size of the matrix is quadratic, so it's linear number of rows, linear number of columns, the number of non-zero entries is actually linear in the input size. So I'm going to skip all the cryptographic part. So we basically have some kind of a matrix construction like this. When we want to do efficient linear algebra that is just based on this matrix construction, then actually computation is very simple. You can use sparse matrix representation. You just basically, you know where the non-zero elements are going to be to some extent. You just store those things. If you add up different rows, different blah, 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 everything is, the computation is basically linear. It's a bit more linear than that because you need to do a few more difficult operations. But those operations are all connected to cryptographic part to some extent. So what is the cryptographic part about is that, so here, like I mentioned that in this previous work they constructed or they defined a more advanced computational model which was called quadratic span programs. And you can kind of a quadratic span program is also it's two matrices, V and W. V consists of those VI vectors, and W consists of those WI vectors. And then you have two target vectors, V0 and W0. And you say that the quadratic span program accepts an input if and only if this holds. And here this circle means entry-wise multiplication of two vectors. So this is quadratic span program accepts an input if and only if there exists coefficient vectors A and B such that this equation holds. Where this is going to be one vector, another vector, and then you have entry-wise multiplication, and the output should be equal to 0. This is actually what this using error correcting codes did. So if at least one of the inputs was, if both inputs were non-zero vectors, then both vectors here, left and right, they will have some coefficient which is non-zero. If you multiply non-zero coefficient with non-zero coefficient, you get non-zero output. So this concrete coefficient will not be equal to 0. And in this case, quadratic span program will not accept X. Okay, so very quickly about the rest. So the idea is that now we can, prover can convince verifier that this circuit has been computed correctly by sending those coefficient vectors A and B to verifier. But it has two problems. First of all, A and B are long, they are linear in length, and we want to get something very short. And the second one is that it violates privacy. So we don't actually want verifier to get to know A and B, we want verifier to get to know only whether this circuit was acceptable or not. So this uses several cryptographic tricks. The first one is that there's, instead of A and B, we actually send to the verifier only V and W such that V plus V0 times W plus W0 is equal to 0. So we basically send this sum and this sum. And then there's a somewhat complicated proof that shows that this is still a good proof, blah, 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 blah. The problem here is that this proof is still long. And then we use crypto to get this more efficient. It uses pairing-based cryptography, elliptic curves. You actually, instead of a vector, you think of this vector, the long vector of this matrix as the number of evaluations of some polynomial, then you use polynomial interpolation to compute this polynomial. And then you actually, instead of the vectors, you operate with polynomials, but actually you don't send the polynomial, you send the valuation of the polynomial at some secret point. So you send, like, instead of one long vector, you send one short element. And there are several other optimizations. I have absolutely no time to go into this. But like I mentioned, like efficiency point of view, the number of operations that has to be done is relatively nice. So the size of the CRS is n log n, where n was the number of gates. This interpolation, multi-point evaluation, or like this polynomial algebra that has to be done, it takes n log squared n operations. And then verifiers computation is bounded by the number of exponentiations that is basically linear in the input size. And the communication is 7 group elements. Maybe those numbers seem a bit mystical, so let me show this application to the case of verifiable computation. What is different here is that, so Alice wants Bob to compute some function. So what I was doing previously, the idea was that the CRS was generated first, and then Alice and Bob chose a circuit. So one long CRS was good enough for all possible circuits. But in the case of verifiable computation, Alice just wants Bob to compute one concrete function. So you generate a CRS that depends on the circuit. In many applications, this is a very bad idea, but in this concrete application, it's a good idea, and it gives you very good efficiency. The CRS length is now it's not anymore n log n, it's n. The prover's computation is O. It's basically a linear number of exponentiations, and then the prover has to do polynomial interpolation and multi-point evaluation, which now can be done in time n log n instead of n log squared n. And the maybe most interesting part is that, like in this general case, provers had to do like linear in the length of input exponentiations. But if you assume that this application in verifiable computation, then the prover only has to do 11 pairings, cryptographic pairings, by using elliptic curves. Now this doesn't depend at all on the circuit size. And the communication is still 7 group elements.
But doesn't the verifier at least have to read the circuit or something? I mean, if the verifier doesn't know which circuit?
Well, the circuit is, like I said, the circuit is fixed in advance. So, well, circuit is kind of a read while you generate the CRS in some sense. When you later do the verification, you don't have to do it again. So if you, for example, want to compute for several functions on different inputs several times, you can amortize it. You read the circuit, like you generate CRS once, but every time you verify, if you do verification, then you don't have to do it again. So, to give some more concrete numbers, I have a master student who is currently implementing this stuff. And I don't know how well it has been optimized, etc., but these current numbers are like this. Assume that the circuit has 1024 gates. Then CRS generation takes 48 seconds. Prover's computation takes 21 seconds, and verification takes 6 milliseconds on his laptop. I still have to check how optimized this code is, what happens if he uses my laptop. what happens if he uses actually a desktop, etc., etc. But 6 milliseconds is already quite good. And the only thing to be left is this prover's computation. And so this, and like I said, maybe in between everything looked very, very theoretical, but the end application here is verifiable computation. You outsource your computation to somebody like Amazon and then get back the result together with the proof that computation was done correctly. And this doesn't add much, so prover has to do some more work, but verifier only does like 6 milliseconds, which is nice. And that's it. I was 3 minutes late.
Questions?
Is the
Dominic?
CIS reusable between different tools?
Yes, it's reusable. So if you use the terminology from zero knowledge, then this general case, less efficient case, you have adaptive soundness. And in the case of verifiable computation, you have non-adaptive soundness, which means that you first fix the function and then generate CRS that depends on this function, but you can reuse it many times with the same function. Juris. Questions? No?
So if you let the verify run after 1 second, how big circuits would you be able to verify?
Well, in the case of verifiable computation, like I said, the number of verifiers computation, the time doesn't actually depend on the circuit size. I've been pushing this master student to try larger input sizes to find out what will exactly be the prover's computation, but it seems that he actually runs into memory problems.
It actually might be that the verifier's computation becomes somewhat slow at some point, because if I understand correctly, the CIS needs to be stored at the verifier, and the verifier does random access to the CIS, I would guess, right? I mean, it doesn't read all of it, otherwise it would be slow.
Well, the CRS that verifier needs to have in this verifiable computation case is very short. I don't remember by heart how long it was, but it was also maybe 10, 20 elements. But at some moment when the CRS is generated, the verifier should once verify that this was done correctly.
So the CRS takes a long time to generate, but it's short.
Yes. Well, the CRS, so okay, there are two different CRSs. Prover has a long one and verifier has a short one. But at least once in the beginning, verifiers should check that the also provers.
Okay. So it's like one big public CIS, but the verifier needs only a small part for the verification. Okay.
Well, she needs this long part once to verify it, and then can remove it, and then has only short part, so you can compute the same function many times.
Why would the verifier need to verify the CIS? It's assumed to be generated honestly, right?
Okay, yeah, if it's generated honestly, then you don't have any problem.
And if it's not generated honestly, it's probably not secure.
Yeah. Yeah, actually, yeah, you're correct. You don't even need that.
And the verifier does not need to know the circuit. So
the verifier doesn't need to know the circuit, but then the verifier really needs to assume that CRS is generated honestly.
But essentially, it's a very small device, and it's just put in the CIS, and that's implicitly a circuit description.
More questions?
Okay, next time.